Hello. Welcome to College Math live streaming now with high-speed internet. I hope it looks good, but please let me know if it's difficult. You'll move back a little bit because I think actually it's better if you can move the board, I feel like. And I'm hoping that with my new modem and new internet provider that the sound in the video will be top quality so that you're able to see it. If you're not able to see it, hopefully somebody will let me know through the YouTube live chat. That's the most immediate way to let me know about technical issues if they occur, because I only have the word cloud up right now for the polls, so I don't have you don't have a chat box there yet. But I see all your names and welcome. Thanks for being here. I'm going to just close the window behind me so that I can get rid of the glare here. And there's glare from my screen too, so usually I turn it down, and that's good. It looks a little crooked today. Let's see if I can fix that. Secrets of college math. That's straighten out the computer too. See? So they're multitasking. You can get it to be nice and lined up there. Okay. Cool. I really hope the quality is good today. Got my fingers crossed there. And let's see what we got. Oh, welcome everybody. I see your names in the polls. I'm glad to see you here. And I'm really interested to know that in these last 6 weeks of all the learning that we've done, what are some of your favorite concepts and themes? And I'm going to use that information to help plan out the last part of our curriculum here. Try to speak directly to exactly what you're all most interested in learning. So welcome again. I see all your names there. It's great to see you here and in Zoom. So 1-2 punch is working really well, I feel like. And I'm going to turn it over to the favorite concept so far. And it's set so that everybody can enter 3 concepts into this word cloud. So let's see what your favorite concepts are so far in our program. Whoa, just the math part. Don't forget that in the word cloud mode, you do need to combine more than one word with an underscore so that they don't get broken up. And I see the LE effect floating around, but LE and effect are kind of broken up. That's what happens if you enter more than one word phrase into a word cloud. And then somebody corrected it. Awesome, great. So I see all sorts of stuff popping off in this word cloud here. LE effect seems to be a really big winner. And that tells me that you all are really into the applied part of our math curriculum. It's no surprise because it's so useful. And in my favorite book on differential equations called Differential Equations by Paul Blanchard, Bob Devaney, and Dick Hall, the very first sentence says, "This book is about how to predict the future." That's probably more meaningful in context than theoretically to most people. So that's why I think I see these great comments that speak to the application to ecology. We also have intervention in a complex system, and that's one of the things that I wrote into the applied math problem set today, so we can dive into that. I see some people liking Euler's rule, which is pretty cool. That was unexpected, but it's so useful to be able to numerically integrate and simulate these models. Equilibrium points, differential equations, feedback loops is huge. Yeah, and that is it really, really a big one here. If you want to use feedback loops for one of your key concepts this week, I think that's a great idea because that's been a theme. Every week we're taking it back to feedback. I'm applying what I know about the important great one to tackle. You also see vectors on there, power rules. Some people are loving those derivative rules. Those are fun. Multivariable systems. And let's see, differentials, exponential growth and decay, semi-stable points. Wow, I'm surprised to see that as a favorite concept, but it is so important as a dividing line between stable and unstable cases. So it's cool to see all these different things up here. Awesome. If you're somebody who's like a little worried about this week, what am I going to use for my posts? As usual, this is why we do this on Tuesdays, is so that you can always go back to that Canvas page later today and go ahead and pick out 3 that you're ready and comfortable to explain in your own words and to give an example of this week. And I will write your concept quiz that's going to be due on Thursday based off of all of your posts. So make them nice and juicy, and I will be happy to try to create multiple choice questions based off of those. Awesome. It looks like we're kind of at an equilibrium here with the word cloud. The total results are no longer changing. So I just have a little bit of a quick multiple choice before we open up the open-ended concept. The open-ended chat space. And I think I kind of know the answer for this one, but I put it up there anyway. What should we dive into? Because there's kind of 3 different ways that we could go right now. We could do some review on some of the concepts that you've named. We could talk more about the theory of 2-dimensional equilibrium points, or we can go into the applied math problem set. And I'm kind of just feeling out, it doesn't mean that we have to just pick one of these, but I'm kind of feeling out preferences that people would have for topics, and maybe we'll go into them, by order of preference. But by the end of this YouTube Live, as usual, I will seek to have answered all questions for everybody to make sure that you're nice and set up for a good, productive, and constructive week of learning in ecological dynamics. Cool. Great. And we have 12 respondents there out of our 14 viewers saying that 67% preference for talking about our applied math problems. I think that's where we'll start. That's what people were expressing in the Zooms as what they want to talk about. Then, if you want to start using the open chat space to ask questions about review concepts or name parts of review concepts that you want to see folded into those problems, I'm more than happy to do that. Seems like there might just be maybe one vote for section 3.3 on the mathematical theory of 2-dimensional equilibria. I would also love to talk about that, but I more so want to tailor my teaching to the interests of my student base. Personally, if I was going to pick one, it would be theory of higher order equilibrium points. That was part of my undergraduate curriculum, one of my personal favorite parts. But, it doesn't mean that it's going to be your favorite too. Everybody has their own preferences. And so really, in my role as your teacher, I'm here for you. And I'm here to tailor this to your interests. So let's get started with the applied math problems. And then feel free to diverge onto the other topics as it seems appropriate. But I'm going to open up the open chat space now. And I'm going to let this populate with some questions. So I know some people have had time, hopefully, to read over those problems. And I want to know, what kind of things would you like to see me do? Here, I can do a lot on the board with a chalk talk, and I can do even more afterwards by making a screen share video where I'm playing with the online resources. So the part about using the online resources to simulate the actual equations that I'm asking you to do, I'll make that video when we're done with YouTube Live. But while we're in this space, I can do lots of stuff and tie it in with our current new learning about equilibria in the 2-dimensional state space. I'm just wondering what kind of questions to start it off with. So I'm going to give you all a few minutes to add in your questions to the open chat space, and that will let me know how to get started. I have a math book as usual, and I also have this strangely heavy ecology book. I don't know why this thing is so heavy, but maybe it's the shiny pages. I got both books. Okay, so some people want to hear about my take on higher order equilibria. Ooh, I will definitely love to talk about that. And then we also have requests about Lochte-Volterra competition model. And one thing that just says applied math 2, which is going to be intervening in the predator-prey system. Right. So it looks like most of the questions have to do with the predator-prey model. I think we probably will have time for all three things. I have been known to stay extra. For those who have the attention span to stay, I think we've even hit the 2-hour mark on these sometimes. So don't worry, we probably won't run out of time before we run out of energy. I think that's how it's been going. Looks like most people are asking about questions 2 and 3 in applied math. And oh, thank you for the specific question. Yeah, so what I'm really looking for here in the chat space is an even more refined question, such as someone just said, solving for the equilibrium point, solving for x star, y star, n star. How are we solving for the equilibrium point? That's a really nice specific ask that I can start to talk about right now. And while I do talk about it, feel free to enter more specific questions. Because if you just say like, I want to talk about question 3, it doesn't give me much to work with. You know what I mean? Like, I want to know what part of question 3 or what's your specific curiosity. Let's start with solving for the equilibria. I think that's the best bet. And then let's go on for there. Like someone was saying in the Zooms, we probably have to start diving in and working these problems out before we will know what our specific question is. That was a really good point that somebody made in the Zoom. And so let's just get cracking, and then I'm sure more questions will come up. So I've got the math book here. I'm going to talk about solving for equilibrium points in higher dimensions. That's on page 133. And so if you do have your math book and you want to play along, go ahead and go to page 133, where you will see that they define an equilibrium point as a point where all of the differential equations are equal to 0. It's the same thing as in one dimension, except now we have more equations to work with. And so we have more to set equal to 0. And we have to solve all of these simultaneously. Do you remember that from pre-calculus? Did your pre-calculus teacher ever make you solve simultaneous linear equations, which is finding the location of where two lines intersect in the plane? We're going to do that right now. So hopefully that sounds a little bit familiar to you. Now, I'm not going to go over the problems in the book because those are the most simplest ones, and I'd like to save those for your opportunity to work out later. What I'm going to do is I'm going to start with question number 2 on the Locke-Volterra predator-prey model, and I'm going to solve pre-calc was too long ago. But it's like a bike. You never forget, right? I'm going to solve question number 2, the Locke-Volterra predator-prey model, for its fixed points by setting all the differential equations equal to 0. So I'll illustrate how that works right now. Okay, so predator-prey model. And by the way, if I could just have a little bit of feedback, how is the video quality today? Can you read that? Is that nice and clear? Because I know in the past I had to bring the whole setup closer to the board. Ideally, it's better if you could see both boards so you could see all the writing. But if it's not readable, just type it in and I can make that move again. I was hoping, though, that my high-speed internet would be able to handle it. So if anybody wants to give me a comment just about the technicalities and how readable it is, very clear. Yes, we have finally entered the world of actual internet. Just a little blurry, but hopefully still readable. And the page number, again, is page 133 in the book. It's the very first page of your one section of reading, section 3.3. Great. That's so great. I'm so glad that we finally have some good internet. Okay, I'm going to write down the predator-prey model. Now, I'm not saying that what I'm going to write on the board is on page 133, but I'm going to tie it in with the theory that's laid out in the yellow box on page 133. But really what I'm doing is I'm doing the applied math question number 2. So this is my A math question 2. Okay, and I want to get all the letters right here. For this predator-prey model, I tried to look in the ecology text and align the names of the variables and the parameters as the same as in your ecology text for those who are taking the full load. And so that's why we're going to use the terminology of N being the prey and P being the predator. Okay, so we have two parts of the model. The rate of change for the prey, this is the prey. And then the rate of change for the predator is going to be dp dt. Okay, and the secret is we've actually been working with this ever since the very first video about the snail tail. The oscillations that I showed you there were an example of a predator-prey model where the prey is assumed to be growing with, at first glance, unbounded growth. And then the predator starts eating it. Right? So here we have the prey dn dt, and in the absence of any predation, the prey is assumed to be growing exponentially. Okay, so growing exponentially, I'm emphasizing here with a positive parameter r, that's going to be the continuous growth rate. And there's our classic feedback equation, dn dt equals rn, which now you know the solution to is exponential growth, right? If this was the only thing I had, and I just had a one-dimensional system, that's the equation I had, the answer would be n sub 0 e to the rt. Okay, but we're also going to add in predation. And so that's where the minus a times np term comes from, right? And remember that if we're going to model interactions between two different species, those interactions are going to take place probabilistically at a rate that is proportional to the product of the two population sizes. So that's why we have n times p here, because that's modeling interaction. Interaction will happen at a rate that's number of prey times number of predator. And then there's some coefficient, right? The coefficient of proportionality here, A, is, I think the ecology textbook called that like the efficiency, the predation efficiency rate or something like that. So, you know, this number A is probably going to be less than 1, and it's going to be whatever the level is, like how efficient the predator is. On the predator equation, remember how we said that prey is going to be doing exponential growth? Well, the predator is doing the opposite. It has exponential decay in the absence of prey, because we're assuming for this model that the prey is eating the, oh, dang it, I said it wrong again. The predator has exponential decay, because if there's no prey, the predator is going to go hungry, and then it is going to decay at a rate proportional to its membership. That's where the minus MP comes from. The predator has nothing to eat, and it's just going to die with no prey. That's what that's about. And then this other term that you see on the equation is, it's the same ANP. It's the same term from right up here brought down to the line of the predator, where you can see that there's a minus here for the prey, because the prey are being taken out of the system. They're getting reduced by interactions with the predator, but the predator is gaining from the situation. And so that's why it's a positive, where before we saw negative. And then there's this extra letter here, B, this extra parameter that's multiplying the term. And B is kind of like the efficiency rate at which the predator is ingesting the prey, right? So this is the A has to do with the efficiency of the predator catching the prey, and then multiplying it by B, another parameter, is like how much food are they getting out of it after they caught it. So that's why it's a B times A here. Mathematically speaking, I could just take this product, B times A, and just name it as like some other parameter. I could have just called this beta in front of the NP, but ecologically speaking, it makes more sense to have the product of two parameters here, because then you can see that this chunk here was taken and it was directly folded into the benefit of the predator, and then times another term that says how good they are at eating it or processing it. Okay. So that is a little bit of review of the equations. Hopefully that's all good. Go ahead and keep putting your comments and questions in the chat if you have any. And now I will show you how to solve for equilibrium a la page 133. Okay. So solving for the equilibrium points, we're going to set these things equal to 0. Equal to 0. You see, I'm just setting the differential equations equal to 0, right? It's the same thing that we had before. I'm going to repeat, actually, before I just write equal to 0, I'm going to repeat the equations that I had. I am going to set these equal to 0, but before I do that, I'm going to look at my equations and see if it's possible at all to write them in a factored form. That's going to be really key to our ability to solve for equilibrium points. Is maybe we can take these polynomials, these nonlinear expressions here, and we can write them in chunks that are times each other. That's called the factored form. And the great benefit to the factored form is that when you set a factored equation equal to 0, all you have to do is guarantee that one of the factors equals 0. Because, you know, if you have a string of 10 numbers and one of them is 0, then multiplying all those together will still be 0. So it would be really helpful if we can write out these chunks as factors. And you can see on this first line that there's a common factor of n. Okay, so if I wanted, I could take an n out and I could write it like this. If you don't believe me, go ahead and factor it back out and you'll see that you got the same thing that you had before. It's going to be nicer to solve for the equilibrium in this factored form, though. That's why I'm doing that. Again, down here, there's a common factor of p. And so I'm going to write p, and then I'm going to do b-a-n minus m. Okay, and then I'm going to set those both equal to 0. Okay, and now we're going to solve for the equilibria. And like I was saying, in this factored form, the advantage is that, like for this first line, all I have to guarantee is that either this term equals 0 or the other term equals 0. Either way, I'm going to get 0 out of that equation, right? So this gives me two things. Either n equals 0 or r minus ap equals 0. Right? And same thing over here. There's two different branches we could take. Either p equals 0 or b-a-n minus m equals 0. Does everybody understand how I branched that out? If you have any questions, throw them right into the chat. Now I have choices to make. So now I have to kind of go on each different path and make sure that I pick one of the choices. So I'm going to go back to this board and I'm going to do that part of it. Okay. Remember when there used to be fancy restaurants you could go eat in? And sometimes they would have a prefix menu and they would say, choose one appetizer, choose one main dish, and choose one dessert. That's kind of what we're going to do here, okay? So we're going to choose one way to make the dn/dt equation equal 0. We're going to pick one of these ways for our appetizer. And then for our main dish, we will pick one of these ways for the predator equation to equal 0. And so we're going to do a mix and match, and we're going to end up naming all the different, I know I used to, we're going to enumerate all the different possible equilibrium points by picking one thing from the top equation and one thing from the bottom equation. The most important thing about this, and this is kind of why I bring up the menu example, is that when they give you that choice on the menu, they're telling you to pick one appetizer and one main dish. You can't just pick two appetizers. You can't have both main dishes, okay? You got one of each. And that's what we're going to do here. We're going to pick one way for this equation and one way for that equation. We can't just go into one of them and say, okay, I'm going to take both of those. That's not going to work out, okay? So we're going to find all the equilibrium points by taking 1 root for dn dt and 1 for dp dt. We got to take one of each. And each one actually has 2 choices. So now's the time for you to play the game with me. How many equilibrium points are we going to have in the plane? Because I could pick one out of those 2 things. And then I could pick one out of these 2 things. You could just guess if you can't add it up yet. Just give me an idea. How many different equilibrium points do you think we're going to end up with? It's the same thing as saying if I gave you a choice of 2 different appetizers, 2 different main dishes, how many different meals could you make out of that? It's a little bit of combinatorics from discrete math. 4 different ways, exactly, right. We're going to have 4 different equilibrium points, and so we can graph all those in the plane. Great job. Okay, so we're going to end up with 4 different equilibrium points all together. Excellent job. Okay, now the first point is probably an easy one. It's sticking right out there, but how about we make this more interactive and have you throw it in the chat? Somebody want to give me a name of one of the equilibrium points in the format n comma p? Okay, because remember that these are 2-dimensional equilibrium points, and so the format is going to be n star comma p star equals, and go ahead and name any of the equilibrium points in that format, n comma p. There's one that's probably the easiest one to pick because it's already solved out for n and p. You can see that, right? I have n equals 0 there, and then I have p equals 0 there. The other ones are going to be a little bit harder, but you're exactly right. 0, 0, right? So the easiest thing to choose would be I'll take n equals 0 for my appetizer, and how about p equals 0 for my main dish? And there you go. You got 0, 0. Right. Now, besides that, the other 3 choices are going to involve at least some kind of combination of one of the second choices there. And I haven't solved those for the variable yet. So now what I want to do to make sure that this is really clear and complete is you see this equation here that says r minus ap equals 0? We're going to solve that for the variable. What do I get if I solve this linear equation right here for the variable? I don't want to say which letter is the variable because we're in review mode this week, and one of the questions on one of your homeworks one time was look at a system and pick out what's a variable versus what's a parameter. Remember that? So I need to solve it for the variable, right? And I see somebody has solved it for r, but r is a parameter. And then someone solved it for p. Excellent. P is the variable. The variables are the things that are getting ddt'd. You see, so dn dt and dp dt, the variables are n and p. And so I want to solve that bunch of letters for the letter p. So here I get p equals r over a, p star. Right. Good, good. And now let's do that to the other equation too. This one right here, can you solve that for the variable? That one has even more letters. What happens when we solve this one for the variable? What do we get? So solve it for the, I'm going to wait till somebody puts it in. It's my hope that you're trying to do this on pencil and paper a little bit to start to play around with it. This might even be in your ecology book this week. Right, so we're going to solve this equation as well for what the variable is going to be. Perfect. Right, the variable is n, and so we get n is equal to m over ba. Yes, you're all doing a great job there. All right, so the n star is equal to m over ba. Great. You see, now that I've solved each of these for the variable, now I can play my little menu game and I can mix and match for the other 3 fixed points. And somebody already named one of the other fixed points. If I happen to choose the second choice for this and the second choice for that, then the thing that I would get for my equilibrium point would be n is equal to m over BA. So m over BA for the n. And then P is equal to R over A. So I could have, this is another fixed point. 1 fixed point, 2 fixed points, or like you all said, there's 4 fixed points altogether. So right now we have 2 of the fixed points on the board. We have 0, 0, and then we have, if I choose the second route for each, but what are the other 2 fixed points? There's 2 more combinations that I could make. I could go the top route for one of them, and I could go the bottom route for the other one. So let's enumerate all the equilibria that way. What we're doing right now, we could also apply to question number 3. And in fact, next week in math, when we go on to section 3.4, the process that I'm doing right now is the starting point for next week's learning. And so practice along with me, even if it's not being asked of you for your homework set, knowing that this is going to be the first step in a much more mathematically complicated process that you're going to learn next week in 3.4. Right, so I could go 0 for one of them and R over A for the other one. Right, so if I picked n is equal to 0 for this one. Hold on. Oh, this is getting so confusing. Remember, I can only pick 1 appetizer and 1 main dish. Okay, so one thing that you really got to watch out for, which I want to flag as like it's a thing that could happen, but it's not going to be a real fixed point, is if you pick both of these at the same time, that's not a fair pick, because that would be like you picking 2 appetizers, right? So if I want to pick n equals 0, I can't also pick P equals R over A. That's not fair. That's 2 appetizers. And so actually this seemed like easy to do, but when you really try to do it, it is a little bit hard to do. Okay? So if I want to pick P equals R over A, then wait a minute. Now I'm getting confused about this. Okay, so if I pick n equals 0 over here, then either I have to, oh, wait a minute. Oh, geez. Oh, geez, something's getting messed up here. Oops, my bad. Right. Okay, so, so I get to pick, oh, wait, but P, oh, geez. Oh, this is so hard. Something weird's going on here. Something really weird's going on here. I didn't expect this live. Maybe I should have worked this one out first. Okay, so this is where it gets confusing, and we are going to do this again next week, but we have to make sure that we only pick one of each, right? So if we pick this choice, we're actually not allowed to pick this choice. So that means that if we pick this choice, now we have to pick one from here and one from here. But one of these says P equals 0, and the other one says n equals m over BA. But I already picked n equals 0. So I can't pick that one. You see the little pickle I'm getting myself into here? So it seems like I've only got 2 fixed points. I thought I was going to have, I'm confused too. It's okay. It's okay. Being confused is part of the process. I've actually confused myself 100 times probably on the same exact problem, and that's how you learn. Okay, so that's a good feeling to have right now, kind of like when you're in a yoga class and they're like, you're supposed to be comfortable and uncomfortable at the same time. I feel a little uncomfortable right now. I feel a little confused, and that probably means that I'm learning something that's hard to learn. That's exactly what's happening. So like I was saying, we all thought that there could be 4 of them, right? It seemed like there's going to be naturally 4 different fixed points to pick. but 2 of them were easy to pick. When we start to write down the other 2, we get in a pickle. Because if I pick this one, n equals 0, right? Okay, I'm going to pick choice number 1 for the appetizer. I would put it right here, right? But then if I want to pick choice number 2 for the main dish, that's a definition for n. But I already picked n equals 0. So I actually can't pick this. The only thing I could do is stick with my 0, 0 point. So you know what? There's not another fixed point to pick there because I got stuck in a pickle. Let's see what people are saying about that. Can you pick n equals 0 or n equals m over ba and p equals 0 or p star equals r over a? You can only pick one from the top and one from the bottom. You can't mix and match any old way that you want. And that's the problem for fixed points. Is because the thing that we're trying to choose is we're trying to pick one way to make dn dt equals 0 and one way to make dp dt equals 0. And if we pick from the top here, n equals 0 and p equals r over a, if we try to do that at the same time, the only thing we solved was dn dt equals 0. If we don't pick anything from the bottom row, we're not making dp dt equal to 0. So I actually, I thought we could pick 0 and then p star equals r over a. So I thought this was an okay way to go, right? But this is actually not an okay way to go because if I pick that, the only thing I did was I only set dn dt equal to 0. I didn't pick one of these, you see? So I didn't make them both equal to 0 at the same time. So that's not cool. It's okay. We're learning. Likewise for this, you might think it would be a good idea to pick n is equal to b over a, right? Like I would think that's a reasonable choice. M over ba. And then if I had to pick another one, so I picked this one, if I have to pick one of these for p, it says that p is equal to r over a. Oh, wait, I already had that one. If you want to pick both of these, it seems reasonable at first glance. But it turns out if you pick both of these, all you're doing is you're just setting dp dt equal to 0, and you're not letting dn dt also equal to 0. So this seems like a choice, but it's not an okay choice. I thought there's going to be 4 fixed points, but there's not. There's only 2 different fixed points. There's only 2 different equilibrium points because I got in that pickle. Let's see what the comments are. I'm actually glad we got this confused and needed to work it out because now I'm convinced. I would have made the same mistake on my own, and I just did live. I didn't plan this. It just happened. This happened to me so many times. It's okay to make mistakes. That's how you get really good at something, is that you have that icky feeling and you just keep going. So we just made a really important mistake, which is that we thought we could get 4 fixed points, but when we really tried to choose our menu, 1 appetizer and 1 main dish, we weren't able to result in 4 unique fixed points. We got ourselves in a pickle with the last 2 fixed points, and we're only able to pick these 2 different fixed points. Yeah, you know what? Geez, I really wish I had the phase plane, or what they call the state space. I really wish I had a visualization of what I'm talking about here with the vector fields. For that, I would have to use the online resource that I shared with you. And when we're done with the YouTube live part, I'm going to make a video of me sharing my screen and talking this out as I use that online resource. And I will explain to you exactly why this happened and how that appears on the phase plane. Okay. I'll show you, I can show you a little bit right now, but I won't be able to draw all the tiny arrows. So let me illustrate it a little bit for you now. Hopefully everybody feels okay that we got confused, but now hopefully it feels like It's understood. Is everybody understanding why we only found only 2 equilibrium points? I hope everybody understands why these 2 on the bottom that I crossed out do not count. The reason that these bottom 2 do not count is because for each of those bottom ones that I crossed out, it only sets one of the 2 equations equal to 0, and the other one is not equal to 0. That was the problem. I'm going to draw the state space right now, but it's going to be also really good for you to see the video that will be uploaded later tonight, where I have an illustration of the state space with the vector field overlaid using the online tool. So I'm not going to be able to do it justice on the board. But I'll give you kind of a starting place, which is that, for one thing, the state space is two-dimensional. There's 2 variables. Usually, the first equation is what we use for the horizontal axis, and the second equation is what will be used for the vertical axis. And because this is an ecological model where these 2 variables are representing populations, that's why I've only chosen to focus on the first quadrant where both of the variables are positive. It wouldn't make sense to focus on negative for either of the variables. One of the fixed points is right here at 0, 0. So this is one of my fixed points. And the other fixed point is where n is equal to m over BA and p is equal to r over a. And I'll just graph that like that. So this is the point where we have m over BA, comma r over a. Okay, so there's a graph of the 2 fixed points in the state space.